Raise a complex number to a power, and something geometric happens. Watch one arrow scale and turn, then do it again and again. A high power can race around the plane before landing somewhere surprisingly simple. Reverse the question, and the landing point may have several equally valid starting arrows. Powers move forward, roots reconstruct every possible way back. Recall our compact address for a non-zero complex number. Z equals r e to the I theta. Place its arrow in the plane. The positive number r gives its length, while theta gives its direction. Read the same point after one complete turn, and theta may be replaced by theta plus 2 pi. That repeated address will become essential when we solve for roots. Multiply two polar arrows. Their lengths multiply and their angles add. Stretch first by r1, then by r2, and the total stretch is r1, r2. Turn first by theta 1, then theta 2, and the turns accumulate. Repeat one identical multiplier. Every copy contributes another scale and another rotation. A positive integer power is repeated complex multiplication. Test the machine on 1 plus I raised to the 8th power. Rewrite 1 plus I as square root of 2 times e to the I pi over 4. Scale its length 8 times. Square root of 2 to the 8 is 16. Spin its angle 8 times. 8 times pi over 4 is 2 pi. One complete turn. Land on the positive real axis. The result is 16. Build the general pattern using only positive integer powers. Start with z equals r times e to the I theta, and multiply n identical copies. Count the lengths. R times r, n times, gives r to the n. Count the turns. Theta added n times gives n theta. Predict the output. Z to the n equals r to the n times e to the I n theta. Package the same idea on the unit circle, where r equals 1. Expand e to the I theta as cosine theta plus I sine theta. Repeated multiplication gives open parenthesis cosine theta plus I sine theta, close parenthesis, to the n, equals cosine n theta plus I sine n theta. Name this de Moivre's formula. It records exactly what the turning machine already showed. Compare the two controls. Increasing n changes length through r to the n, and direction through n theta. Shrink an arrow with r below 1, and successive powers collapse inward. Enlarge one with r above 1, and they surge outward. Hold r at 1, and powers stay on the unit circle, hopping only by angle. Rotation can cycle even while size stays fixed. Sweep the power dial through 1, 2, 3, and onward. The arrow at each step is the previous arrow multiplied by z. Wrap an angle past 2 pi, and the visible direction repeats, though the accumulated angle keeps growing. Reset the dial, and the orbit begins again. This many-to-one wrapping is why reversing a power cannot usually return a single answer. Reverse a specific power. Solve w cubed equals 1. Ask for every arrow whose length and angle become those of 1 after 3 identical multiplications. The length must be 1, because 1 cubed is 1. But the angle has several candidates hidden by full turns. Unwrap the circle into an angle ribbon, so those turns remain visible. Set the target 1 at angle 0 on the ribbon. Mark the same target again at 2 pi, 1 full turn later, and again at 4 pi. These are 3 angle addresses for 1 point. Continue to 6 pi, and the eventual starting direction repeats, so the first 3 addresses are enough. The ribbon preserves information, the wrapped circle hides. Divide every target angle by 3, because cubing triples an angle. 0 becomes 0. 2 pi becomes 2 pi over 3. 4 pi becomes 4 pi over 3. Plot those directions back on the circle, and 3 equally spaced arrows appear. Stop before 6 pi. Dividing it gives 2 pi, the first direction again. Exactly 3 distinct cube roots remain. Translate the 3 arrows into rectangular form. Place the first at 1. Place the second at -1/2 plus square root of 3 over 2i. Place the third at -1/2 minus square root of 3 over 2i. Check each answer by cubing. Its unit length stays 1, and its angle triples to 0, 2 pi, or 4 pi, all the same visible point. Choose any non-zero target z equals r times e to the I times theta, with r positive, and seek w to the n equals z for a positive integer n. Write every answer as w sub k equals r to the 1 over n times e to the I times the open parenthesis theta plus 2 pi k close parenthesis over n. Advance k through 0, 1, up to n minus 1. Collect exactly n distinct roots. The next k repeats the first direction. Set the target to 1 and vary n. Draw n equals 2. The roots are 1 and -1, opposite ends of a diameter. Change to n equals 3. An equilateral triangle appears. Advance to n equals 4. 1, I, -1, and -I make a square. Every root lies on the unit circle, and neighbors are separated by 2 pi over n. Dial n to 5. Plot angles 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5. Connect neighboring tips. A regular pentagon locks into place, centered at the origin with one vertex at 1. Rotate from any root to the next by multiplying by the same unit complex number. Switch to n equals 6, then 7. Count 6 vertices in a regular hexagon and 7 in a regular heptagon. Notice what never changes: equal angular spacing, equal radius, and rotational symmetry. Conclude the sweep from n equals 2 through 7. The roots of unity form regular n-sided polygons, including the easily missed 5-sided case. Replace the target 1 by -1 and solve w to the 4th equals -1. Lift the target angle from 0 to pi before dividing by 4. Plot pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Compare with the 4th roots of 1. The same square has rotated by pi over 4. Changing the target phase rotates the entire root polygon. Define omega as e to the 2 pi I over n. Generate the roots of unity with the integer powers 1, omega, omega squared, through omega to the n minus 1. Step repeatedly by multiplying by omega. Each step rotates exactly one vertex. Close the orbit after n steps because omega to the n equals 1. Distinguish omega as primitive. Its smaller positive powers do not return to 1, so it visits every vertex before closing. Carry this geometry to a simple quantum particle moving around a ring. Trace one lap with position angle phi, while a phase arrow turns m times as fast, giving the phase factor e to the I m phi. Demand an ordinary single-valued wave function. After the position returns to its starting point, its complex value must also match its start. Try m equals 2. Complete one lap, so phi increases by 2 pi. The phase advances by 4 pi and returns to its original arrow. Change to n equals 2.5. Follow one lap and the phase advances by 5 pi, landing opposite its start. Reject that pattern under this ordinary ring condition. The same position would receive 2 different values. The boundary filters allowed phase windings. Connect the condition to roots of unity. Closure requires e to the I 2 pi m equals 1. Select whole number windings for this simple, single-valued ring model. Other quantum systems can carry different structure, but this example isolates the geometric idea. Return to our machine. Powers multiply angles, roots distribute possible angles, and a closed loop tests whether accumulated phase lands exactly where it began. Climb back through the lesson. Positive integer powers repeatedly scale and rotate. Roots reverse that motion by keeping every angle address separated by full turns. Ask one last inverse question. If an exponential lands at a complex number, which input produced it? Solve for the exponent, and the angle ribbon never ends. Adding any whole term gives another answer. Open that door next time with the complex logarithm.